Hello, everyone. This is Seok Jang from Queens College and Graduate Center of the City University of New York. You are on the third workshop on quantum matter equations being organized by the Initiative for Theoretical Sciences at the Graduate Center. This is the third workshop on quantum matter equations. We have experts trying hard to make this quantum matter equations approach for more general condensed phase quantum dynamics simulation methods. Before I start, I want to tell you that a few important rules. When the speaker gives talk, please submit your questions by chat to everyone. And then I'm going to get the questions and then ask for you at the end of the talk. So each speaker will be given 30 minutes, including short questions and answers. In case you have longer questions, or if you want to have more extended discussion, please wait until the end of workshop, because we are going to have informal discussion at the end of all the talks. Without any recording, and often that is more informative and more interesting. So please don't go away after the end of talk. With that, let me introduce our first speaker and also co-host of the workshop, EITAN GEVA from University of Michigan. EITAN, why don't you go ahead?
So thank you, Sagi, for this nice introduction. I was just telling the other speakers of this session that, I was reminded today that my first ever paper was about 30 years ago, and it was about quantum master equations. And this is a topic that I've come back to, every several years. And actually, this is now a period where we are, doing a lot of research in this area. So today I would like to tell you a little bit about our work on quantum master equations for simulating the dynamics of electronic observables. And let me start out with some motivation. The kind of processes that we are thinking about when we develop those quantum master equations, even though we are not there yet in terms of actually applying them to many of those systems, are systems like this one, for example. This is a catenuate porphyrite C60 triad that is in liquid solution, THF. And the process that we believe happens in this system, which is a model system for photosynthesis and for photovoltaics, is that you photoexcite the system. The porphyrin in this case is photoexcited. It's a pi-pi star transition. Then you get charge transfer. So this is what I mean by, electronic observables. This is basically electronic energy, charge, and sometimes also coherence transfer. And of course, this is a model system for photosynthetic systems. Here is the FMO light harvesting complex. Here is the bacterial photosynthetic reaction center, and also for organic photovoltaics that many of you are familiar with. So this is the kind of system I have in mind when I think about the quantum master equations that I'm developing. And of course, you need to start from the Hamiltonian, and the Hamiltonian that we often think about when we write down those equations is this Hamiltonian. Basically, we have the electronic states that are diabatic states, and they can and often include charge transfer states in the system that I just showed you. Then we have the nuclear Hamiltonians that are electronic state specific, and I'm emphasizing that they do not need to be harmonic. Many people use models where those are harmonic Hamiltonians, but I would like to think in terms of a more general formulation where those can be expressed in terms of force fields that can be anharmonic force fields, including Coulomb interactions, Jones interactions, and so on. We also, so R and P, basically, the capital R and P are the nuclear degrees of freedom, the coordinates and the momenta. And finally, there is the coupling terms between the electronic states, because those are not eigenstates, those are diabatic states. And they can be and should be oftentimes dependent on the nuclear coordinates and do not have to be linear, as in many models, okay, in terms of the coordinates of the nucleus. Now, to model those kinds of systems, the way I see it, there are basically three grand challenges, and they're interrelated. There is, of course, the electronic structure challenge. That is a huge one, and there's been a lot of progress over the last several decades in this department. But the quantum master equations enter when it comes to the two other challenges. And those are the quantum dynamics challenge and the connection to experiment, I would argue, challenge. And I will elaborate on this in a minute. So, you know, the way I see it, quantum master equations offer, okay, a very appealing and attractive pathway to addressing the quantum dynamics challenge and the connection with experiment challenge once the electronic structure challenge has been addressed. Basically, the electronic structure challenge, the way I see it, is a way to parameterize the Hamiltonian I just showed you in the previous slide. Now, the way this works, okay, is like this, okay? So when we teach quantum mechanics, like quantum 101, this is how we usually teach the students how quantum mechanics works. We say, give me the Hamiltonian, then solve the tiny Schrödinger equation. Usually you have to do it if you have a system in thermal equilibrium over many, you know, initial wave functions, because you have thermal distribution initially. And then, you know, calculate expectation values. But if you think about this more carefully, you realize that there is a huge redundancy in what we do, right? We have this huge amount of information that is in the wave functions. But then we end up with predicting stuff like spectra, like rate constants, like memory kernels, like correlation functions, which are much more reduced dimensionality. So the question is, can you basically not go through this impossible really route, okay, for complex systems of solving the tiny Schrödinger equation and doing this extensive averaging, and just really find, you know, a more direct way to the actual quantities of interest? So the way I see it, quantum master equations start from asking the question in the following way. Basically, tell me what is your reduced dimensionality quantum quantity of interest. And this can be an expectation value. This can be a bunch of expectation values. This can be a correlation function, because many spectra and rates are given in terms of correlation functions. This can be a bunch of correlation functions. This can be the reduced density matrix of the electronic degrees of freedom in the system I just showed you. And then ask the following questions. What is the minimum I need to know in order to, about the overall system, in order to simulate the dynamics of the quantity of interest? How accurately and cost effectively to calculate it in a complex molecular system? And I would argue that quantum master equations offer, you know, a very good pathway to answering those questions in a very rigorous and systematic and improvable way. And I'm going to focus mostly on the generalized quantum master equation, which is basically, at least in my terminology, the exact equation of motion for the quantity of interest, which is, you know, a good place to start, because it's the exact formulation of what I'm asking and trying to answer here. So let me give you a little, you know, overview in case you haven't seen this before. You will need a reminder about generalized quantum master equation and really the Nakajima-Zwanzig formalism. This is a pretty old, okay, theoretical framework. I think the Nakajima and Zwanzig papers are from 58 and 60 of the previous century papers. The idea goes like this. Basically, you define a projection operator, which can be anything in any operator P whose square is equal to the operator itself, because the projection of the projection is, I mean, you didn't do anything. Then you define also the complementary projection, which is unity minus the projection. It is, you know, clear, hopefully, that P plus Q is equal to 1, and P times Q are orthogonal, basically, equal to, okay, 0. And in our context, P projects onto the quantities of interest, and Q projects onto everything else, okay, that is not the quantity of interest, basically. Now, it's a pretty simple, okay, exercise to start from the Liouville equation of the overall system. So basically, you assume that the overall system, the huge complex system, is a closed system, and it satisfies the Liouville equation. And here is the Liouville equation for the density operator. And then the exercise that Nakajima-Zwanzig basically went through is asking the question of what is the equation of motion of the projection of rho. So P operating on rho is the projection. And it's not difficult to show that the equation of motion of the projection, not surprisingly, also depends on what you projected out, because they're still coupled to each other. You cannot just throw out stuff and forget about it. So you can write two equations, one for P rho and one from the complementary projection Q rho, and there are two coupled linear differential equations. And the next step is the most important step probably, is to realize that the equation for Q rho is a linear first order inhomogeneous differential equation, which we know how to solve. There's a formal solution. Here it is. Once you solve for Q of rho in terms of P of rho, you can stick it back in this equation, and you got the so-called Nakajima-Zwanzig equation. So this is the equation of motion of the projection, P rho, that is given only in terms of the projection. So there is no more Q rho in this equation except for Q rho at time 0. And it has three terms basically on the right-hand side. One is what you would maybe expect naively to be the only one, basically the projection of the Liouville. So this is the projected Liouville. This has the Liouville equation form. Here it is. The second term, is more interesting. This is basically the memory of P rho, from time 0 to the present time. And this is really the price you pay for projecting out stuff. If you want to project out in space, if you want, you have to remember the past. You have to go to the past, and this basically tells you how to do it. And this is also a memory term of the initial preparation. So this is the initial state, and how you prepare that, can affect your present state and the rate of change. Now, to show an example, if you choose, for example, a projection that is basically tracing out the nuclear degrees of freedom and focusing on the electronic degrees of freedom. So this is the projection. And if you assume that the initial state is a product state, by the way, both are choices. You can make other choices, but those are very commonly done choices. Then you can use the Nakajima-Zwanzig equation to derive this generalized quantum master equation for the reduced density matrix of the electronic degrees of freedom. So as long as you are asking questions about the electronic degrees of freedom, they can be answered if you know the reduced density matrix of the electronic degrees of freedom. Here is the projected Liouville term. This is what happens to it. You basically get some kind of average over the nuclear of the Liouville. And here is the so-called memory kernel. The memory kernel, is formally given by this expression here. I will come back to this in a minute. There's also this inhomogeneous term that comes from the initial preparation, but for this choice of projection and for this choice of initial state, it happens to conveniently disappear. So it allows us to basically focus on this equation. And this equation really answered the question I started with, namely, what is the minimum I need to know in order to know, the impact of the nuclear degrees of freedom here on the electronic degrees of freedom? The answer is the Liouvillean, the projected Liouvillean, but more importantly, the memory kernel. The memory kernel, is this object, that contains all the information I need to know about the nuclear degrees of freedom in order to understand their impact on the electronic degrees of freedom. There is no approximation here. This is an exact equation of motion. This is important to remember. And, K, if you look at this more carefully, is a super operator that can be represented by an n squared by n squared matrix, where n is the number of electronic states. So if you have, for example, a system with 2 electronic states, this is going to be a 4 by 4 matrix. If you have a system with 10 electronic states, this is going to be a 100 by 100 matrix, but still a much more reduced dimensionality object than, the full Hilbert space of the overall system. Furthermore, K, for complex systems especially, is known to be relatively short-lived. So it's not only compact in space, but also compact in time. And this actually is a very useful aspect going forward. Now, in the not so distant past, people usually use this Nakajima-20 generalized quantum master equation as a gateway to get perturbative quantum master equations. And we've actually heard in the previous workshops on quantum master equations a lot of discussion about those kinds of equations. Here is an example when you have a harmonic buff. Okay, when the nuclear Hamiltonians are harmonic, then you have things like Forster quantum master equation, Redfield quantum master equation, modified Redfield quantum master equation. Those are all basically based on different breakdowns of this Hamiltonian, okay, into zero Hamiltonian and perturbative Hamiltonians. And I'm listing them here. I'm not going to go into details, but this is one pathway to go, which is very useful. What I would like to focus on is the path which is non-perturbative. Basically asking the question, if this is the exact equation of motion, how am I actually going to calculate the exact memory kernels or close to it, non-perturbatively? And about almost 20 years ago, okay, we wrote this paper, me and Xiangxi, my first postdoc, where we showed that you can actually get the exact memory kernel from this equation. It's a Volterra equation. And the input that you need, F, is actually projection-free input, okay? So whereas K depends on the projection in the exponent here, F, okay, is a similar object, but it does not have the projection. And this actually helps a lot. So basically, what you need, okay, is, okay, so the projection-free input, okay, this F object corresponds to the minimum you need to know about the overall system in order to simulate the electronic dynamics. And as it turned out, and this was actually surprising to me, and still is to some extent, F, if you actually look at this carefully, boils down to two-time overall system correlation functions. So, I was taught, like many of us, that many things can be written in terms of two-time correlation functions, but usually it's within some approximation method, namely Redfield equations or linear response theory. This is kind of more general because it tells you that if you are interested in understanding only the electronic degrees of freedom, the only thing you ever need to know is, two-time correlation function of the overall systems. And as you probably know, okay, there are many, many methods out there that can give you this. So basically, okay, you can use exact methods, and nowadays there are, a whole zoo of methods: MCTDH, Harkov equation of motion, QAPI, tensor train methods, or you can use your approximate method of choice: mixed quantum classical, quasi-classical methods like ERAN, linear semi-classical, symmetrical quasi-classical, surface hopping, okay, mixed quantum classical UV, and so on and so forth. Now, importantly, because we are trying to calculate two-time correlation functions, and because, okay, those, okay, are basically going to either lose feasibility or accuracy, those methods, okay, at longer times, this kind of works very well together. So we basically use those methods when they are the most affordable or the most accurate. And I will show you examples in a minute. Now, I would like to also point out that the pathway I showed you, this pathway, is just one out of many possible pathways to get the memory kernel. They are all based on Volterra equation and they are in the same spirit. We recently published this paper that we called a roadmap to various pathways to calculate the memory kernel, because there are many of them. And actually, many people in the audience and also some of the speakers contributed to the development of those. So I'm not going to talk too much about this, but basically, importantly, you should know that not all pathways were created equal. This is a quote from the paper. And some may offer advantage over direct application, and some may not, okay? And also, there are some issues with numerical stabilities that, okay, so if you want to learn more about this, I can recommend this paper, okay? And you can see the chart here that, okay, shows you all of those pathways. But I would like to just, because I don't have much time left, okay, I just want to show you a few examples of how this works in practice. So here is the, familiar spin boson model, because it's one of the only models we know the exact results for. And this actually demonstrates the power of this approach. What you see here, okay, is sigma z as a function of time for some parameters. Those parameters were chosen so that the perturbative master equations, either Markovian or non-Markovian, which are in the, the turquoise and the green, are not going to work very well. The circles are the exact results, and you can see that the green and the turquoise are off. The dashed lines, the red, the blue, and the purple, are approximate methods, ERAN fast and two versions of linear semi-classical methods, and clearly they also don't do very well. They start good and they go out of whack. However, if you now use the same methods, you did not change the methods, to actually calculate the memory kernels for the procedures I showed you, look at what happens. The dashed red method, for example, becomes the solid red method. All of a sudden, it works very well. And this is true for the other two approximate methods. So the main message here is that restricting the use of approximate methods to calculate the memory kernel as opposed to using it directly, can lead to much more accurate description, than the direct application. And once again, this is applicable, in case where the perturbative master equations are not applicable. Now, it's not going to always work as nicely as the example I just showed you. Here's an example where it doesn't work as nicely. This is because the buff has become more and more quantum. And the input methods need to be improved to actually do better. So you can see that we still do better than the direct application, dashed line versus solid lines, but it's not longer coinciding with the exact result. So we need to improve the input method in this case. This is another example, for more than a spin boson. This is a glorified spin boson. If you want, this is the FMO model that many of you have used too. And we see the same thing. It's a dashed line, solid line, improvement. So I'm not going to dwell on this too much. By the way, I should also mention that other groups have done work on those kinds of systems, with quantum master equations, and have seen similar results. The last thing I want to touch upon is the fact that you can do generalized quantum master equation not just for the reduced density matrix of the electron degree of freedom. You can do it for many different kinds of projections. For example, you can look at the populations only. You can project out the coherences of the electronic coherences. You can focus on just the coherences and project other populations. Okay, you can see it. Yeah, sorry about that. Okay, so I'm going to wrap it up basically. So basically, like I said, the reduced dimensionality quantum master equation. Here is another example. Basically, you can actually write the quantum master equation for just one population. In this case, the memory kernel is a scalar, and you can write scalar Volterra equations. And in this case, you also need the inhomogeneous term. So you can do the same exercise with the inhomogeneous term. You can actually obtain the inhomogeneous term from similarly developed Volterra equations. And let me just show you some results with this. Basically, I should also mention, by the way, that the projection-free inputs in this case, are subsets of the projection-free inputs from the full density matrix. Here is a very recent results, not published yet, where we collaborated with the group of Victor Batista, who have this tensor train method, thermofield method, to do exact quantum dynamics. So we used it to get the memory kernels, and we did it for multiple spin boson Hamiltonians, using, you see, the full, the population only, and single population. And what this picture is supposed to show you is that in all cases, you get the exact same result, no matter which one we use. If you use approximate input methods, things are not as peachy, Some work better than others, but since I ran out of time, I'm going to skip this. You can keep it for the discussion. The main message, here is, I'm going to summarize basically, is that, generalized quantum master equations are basically a very nice formalism, which is general purpose and for doing, quantum dynamics of open systems. It's not limited to harmonic buffs or to systems with a few, states. It can be useful for, much more general situations. And its combination with approximate and exact input methods, is something that I think is very powerful. And I hope many of you, will consider adopting moving forward. So I should probably finish. Yeah, that's it. I'm sorry about this.
Thank you for making it on time. There is no question in the chat. Actually, I want to ask two things. Why do you think that memory kernel is less sensitive to approximations than the original?
So I think this is an interesting question, and actually it's not always the case. So depending on how you formulate it, sometimes, okay, you don't get any improvement. This is this pathway paper that I mentioned, and Andre here, okay, and also ERAN did, you know, some really nice work on, you know, helping us understand when it's going to help and when it's not going to help. So you really need to be really careful, and we are still, I think, studying this, and I think other groups are studying this, of when this is actually going to be useful. This is not a completely open question, but you know, something that is still work in progress. We do know, okay, for a fact, and we understand, okay, that there are many cases where this is going to make an improvement. Why? Okay, it's you know, depends on multiple things. I think, first of all, the fact that you limit the input to short times helps. But it's not only that. We used to think it's only this, but it's not only that. It's also because the input sometimes include the correlations between the nuclei and the electronic degrees of freedom in the right way, which you don't have in the direct application. And so, and there are probably maybe other reasons that they're not fully, okay, know yet, okay? But the bottom line is that there have been many observations that this actually does improve. And we have some understanding of why, but I think I would say that, you know, this is still work in progress. We need to do some more work to understand it better.
So there are three actually interesting questions. Yuan Chongcheng asked about implementing this on quantum computing platforms. Ignacio Franco is asking numerical stability of different paths. Can you comment on that? And Debra Sigar also asks, so how the methods you show compare to compare in the steady state limit? Yeah, can you answer this question?
Okay, so those are good questions. So about the quantum implementation, the quantum platform implementation. So this is something that we recently kind of dwelled into. So as you may know, okay, so quantum computing, of course, is a big area of research nowadays. And there have been some effort to develop quantum algorithms to simulate quantum open systems. To the best of my knowledge, most of them are based on Lindblad dynamics, which I consider much inferior in terms of level of theory to what we're talking about here. So we, you know, we are working with Victor Batista and Sabri Kais in Purdue University. And there's actually a forthcoming paper, okay, about basically how do you implement this on a, you know, quantum computing platform. The short answer is that it's possible, and you know, and we have done this basically, and we are going to publish this soon. The question by Ignacio is, okay, so like I saw, there are many pathways. Actually, in this paper I showed, we have 30 pathways, which is maybe too many, but this is the way it is. And we have observed numerical stabilities issued with some and not with others. It depends on the input method, so it's still, once again, work in progress. We don't fully understand. We are trying to map this out and to understand this better, but there's clearly issues with numerical stabilities with some methods and not with others. And I can talk about this more in detail, you know, in private conversation or later on in the discussion. Comments, the methods you show compared. So we did not do the steady state limit. And I think in steady state, a lot of the memory effects are going to be gone because those are usually short time effects, no Markovian effects. So in steady state, they may not be that important, but I have not studied yet. So I don't know the answer for sure.
Yeah, there's a last question by Duncan about using n non-equilibrium RPMD plus GQME instead of LSC plus GQME.
Oh yeah, so the nice thing about this methodology, it's not really a numerical algorithm, right? It's a theory, okay? The framework is general. You can implement it with any input methods, including, okay, you know, ring polymer dynamics, okay, which is, if I understand correctly, this is the question, okay? So this, anybody who has a method, okay, which is approximate or exact, to do quantum dynamics, okay, of relatively complex systems, I would say should try this out, because usually it improves the results. Worst case scenario, it doesn't, but at least you can look at new objects like the memory kernel. So I think there is a lot, okay, and I'm actually very interested. You can see, okay, one of the comments here, okay, but in the summary, okay, I think trying this with as many input methods as possible would be very beneficial to this, okay, area of research. And I actually envision this as maybe some platform for developing some package where you can choose, okay, from a menu, okay, which input method you do. Like when structure people choose the density functional or the basis set, right? It can work with any one of those. There's no limitation. And just one last comment, if I may. This is, to me, really an analog of something like, you know, a density functional theory for quantum dynamics, because, you know, if you think about it, density functional theory, one of its reasons for success is because it focused attention from the wave function to the charge density, which is a reduced dimensionality quantity. Okay, we are doing the same thing here for dynamics. The memory kernel is the, you know, the density functional in this case. Okay, we know it exists. Yes, we have to approximate it in many cases, but still, okay, knowing that it exists and what it looks like exactly is a good gateway to actually, okay, finding, okay, approximations that, okay, are better than what we had before. And I will close with this basically. Yeah.
Okay, thank you so much. Our next speaker is ANDRÉS MONTOYA-CASTILLO from University of Colorado, Boulder. ANDRÉS, yeah, please go ahead.
Okay. Thank you so much to the organizers for your invitation. I'm delighted to be here. Today, I would like to tell you about how we can exploit chemical memory, which lies at the heart of generalized quantum master equations to elucidate the dynamics of various types of chemical processes ranging from electron and energy transfer all the way to biomolecular dynamics of protein folding. But before I get into the main topic of my talk, I wanted to give you a broader sense of some of the research that we do in the group. We focus on really elucidating and developing methods to capture the quantum dynamics of charge and energy transfer in disordered chemical environments occurring both in and out of equilibrium. And not surprisingly, we work on really being able to elucidate the dynamics of these excitations in things like molecular aggregates and then material heterostructures for the next generation of lighting, lasing, and solar energy applications, and even understanding and being able to control the decoherence mechanisms in near-term quantum computing devices. As you can see here, a central concern in my group is to develop methods that will also directly allow us to calculate the output of spectroscopy that is being measured in the lab. And that's why here I'm showing you two collaborations with different experimental groups. In the first one, we're working with experimental folks at CSU, looking at the photoelectrochemical activity of things like molybdenum disulfide. And on the right is a collaboration with folks at SLAC who have developed a new type of spectroscopy that gives access to the orientationally resolved dynamics, relaxing in isotropic liquids with femtosecond and an angstrom level resolution. And I want to show you very quickly just the beautiful agreement that we get with the theoretical framework that we developed and the experimental signals. And this was done while I was still a postdoc in the Markland group, and I've continued to contribute to this project. Finally, I'll end by saying that a lot of the work that I'll show you today on the GQMEs was work that I did as a graduate student with David Reichman at Columbia, and then later with Tom Markland as a postdoc. And then these are some of my other collaborators. You'll see ERAN talking about master equations also. And so I'm going to be talking about some of our work together as well. So with that, let me get into the main topic of my talk, which really centers around GQMEs and how we can use them to elucidate a whole bunch of different cool processes in chemistry. And so to start, I know that EITAN already very kindly introduced GQMEs, and I'll do this for the benefit mainly of the students since there are so many experts in the audience. But what is a GQME and why is it useful? Why should we care? Well, I'm going to show you a very simple example. Imagine that I have this box and it contains a fluid of small blue particles, and then in it I drop a big red particle, and I would like to predict the motion of this big red particle as a function of time. Now, clearly, to be able to predict the motion of that big red particle, I need to know the motion of all of the blue particles because they're bumping into the big red particle. But it would be really nice to be able to describe this in a reduced dimensionality context, very much the same way as EITAN described. And we know that this should be possible. After all, this is the basis of a Langevin equation description of this problem. We should get something like a friction constant, and that's precisely what the GQME allows us to do. It allows us to get an exact equation of motion for the variables that we care about. In this case, it's going to be the position and momentum of this big red particle, and it allows me to derive this nice generalized quantum or classical master equation where I can put the position and momentum of the big red particle into this quantity C, and I can encode all of the different interactions of this particle and its environment into the memory kernel. If I did not have this term, this memory kernel term, then what I would have is the description of the big red particle in isolation. So it really encodes all of these highly non-trivial interactions that lead to the complex motions that we would observe. And what I hope to show you in the rest of this talk is how we can use this generalized quantum master equation framework to elucidate a wide variety of chemical problems. And at first, I'm going to focus primarily on photoinduced electron transfer in solution as a way of showing you some of the benefits that we can get by using the GQME framework. So in photoinduced electron transfer reactions, what might be some of the factors that influence the motion of this electron, let's say from this blue ion to this yellow ion? Well, you might say the internal structure of these ions, for example, the energy of the donor state and the acceptor state, as well as the coupling that leads to that electron transfer. In addition to that, you might imagine that there are internal degrees of freedom for these ions, such as vibrations and torsional modes, that are going to couple to the motion of that electron. And in addition to that, you also have this polarizable environment around it, these water molecules that can rearrange so that they can point to their little hydrogen atoms, which are partially positive in these water molecules, toward this negatively charged ion, providing some stabilization energy. So what I've described is hopefully a very complex process, a very complex chemical reaction. And what we would like to do is have a theoretical framework that can capture the anharmonic nature of the potential energy surface that leads to the motions and interactions of all of these molecules, while at the same time capturing the quantum dynamics of this moving charge or the moving electronic excitation. And that's why quantum classical theory is so tempting. It gives you a recipe to do precisely that, even if you can only get the quantum dynamics of the moving electrons approximately. And these methods are not perfect. Let me show you. And this will be reminiscent of a lot of what EITAN just showed us. Here is the probability of finding the electron on the blue ion at +1 versus on the yellow ion at -1 as a function of time. The black line corresponds to the numerically exact result for a simple model of this chemical reaction using the spin boson model. And the different colored lines that you see here correspond to different flavors of quantum classical theory. And the main thing that I would like you to take away from this is that they give you pretty approximate dynamics. They don't look particularly accurate. But you don't have to be satisfied with this, again, as EITAN showed us. And instead, what you can do is solve directly for the memory kernel. And again, here we have EITAN and Cheng's beautiful work from 2004, where they combined LSC-IVR with the GQME, as well as some subsequent work from the Markland group, combining momentum jump QCLE, which ERAN was a key part of, as well as combining mean field theory or ERAN-FEST with the GQME, and then other work that we all did together. So the nice thing is that once you calculate the memory kernel using those same methods that don't give you great accuracy, you can go back to the GQME, you can solve this integral differential equation numerically, and lo and behold, all of those different colored lines that previously looked so inaccurate can now collapse almost exactly onto the numerically exact result. And again, this depends on a lot of things, and I hope to tell you about this a little bit more. But that's not the only benefit that you get. In fact, if you look over here, the memory kernel has decayed by a timescale of 3 of these dimensionless units, but here the dynamics of the electron transfer goes on for over 15 of these dimensionless units. So that means that we only need to use our potentially quite expensive quantum classical theories for this short amount of time, and then we get the rest of the dynamics effectively for free. So it seems like the combination of the GQME approach and quantum classical theory can lead to both improvement in accuracy and improvement in efficiency. And by the time that Dave and I got to this problem, the main question that we wanted to address is, well, where is this beautiful improvement in accuracy coming from? After all, the dominant hypothesis in the field was that this improvement in accuracy was largely coming from the fact that you had short-lived memory kernels and that quantum classical theory was short-time accurate. After all, you can see that the dynamics over here are pretty accurate with these quantum classical methods. So the idea was that if you have these short-lived kernels and the short-time accuracy, you would get the memory kernels accurately for short amounts of time, and then you would be able to get this beautiful improvement. And so we wanted to systematically test this hypothesis. So the way that we did that was, first, let me show you again the results that you've come to expect. Here is the memory kernel for, again, another version of the spin boson model. The black lines correspond to the numerically exact results. The green lines correspond to mean field theory, approximate theory, and the red rhombuses correspond to a GQME combined with quantum classical theory, where the projection operator contains all of the populations and the coherences, the populations being the probability of finding the electron on the blue ion versus the yellow ion, and the coherences being the terms that connect these populations. And you see this beautiful improvement, you see the short-lived kernels. Wonderful. What if we now change the projection operator? What if we now exclude the coherences? Well, you still see that we get this beautiful improvement indicated by the blue rhombuses in terms of the accuracy that we get. And yet, when we look at the memory kernels, we notice that the memory kernels are incredibly long-lived. They are as long-lived as the original dynamics, or the original population dynamics that we were interested in. And so this really demonstrated something very fundamental, right? That long-lived kernels, even in this combination of quantum classical theory and GQMEs, can also lead to this beautifully improved accuracy. And so this really brought us back to the original question: where is this improved accuracy coming from? And that's exactly the question that I hope to answer for you now. So to do that, I need to go back to the derivation of the GQME and maybe use some of the language that EITAN introduced previously and give it a slightly different spin. So the first thing that I need to do is define my projection operator, since this will determine the observables that I will measure. And so here I can define my projection operator to contain this vector A, and in that vector I'm going to include the measurements that I hope to make. So let's say, for the sake of this argument, that in that vector I'm going to include the probability of finding the electron on the blue ion versus the probability of finding the electron on the yellow ion. I'm also going to introduce the complementary projector 1 minus p, such that p plus q is equal to 1 and p times q is equal to 0. They are orthogonal. And I'm going to introduce the quantity that I'm interested in calculating. And this quantity will be the probability at time t of finding the electron on the blue or yellow ion, given that at time 0, the electron was either on the blue or yellow ion. So the stuff that you see on the left encodes the initial measurement or the initial condition, and the stuff that you see on the right is my final measurement. Now, for those of you who might be interested in the meaning of this inner product, it's a quantum mechanical trace over the density of my system. It tells me how to prepare my system initially. The measurement of whatever I want at time 0. So where is the electron at time 0 on the blue or the yellow ion, and also where is the electron at time t. The GQME itself is an equation of motion, so we'll take a time derivative. It brings down an IL. We can introduce a 1, p plus q. Now we get two terms. Let's introduce the meaning of p, which gives us now this quantity, which is the original correlation function that we cared about. And this is a static matrix. Great. This guy, we're going to treat a little differently. We're going to invoke the exact identity called the Dyson identity, which allows us to expand this into two terms. And in EITAN's language, this would give you the inhomogeneous term, but by construction, this term is going to be 0 in my derivation. And this guy is going to give rise to the memory kernel, to this part of the GQME that gives rise to the memory kernel. So congratulations, you've derived either for the first or the millionth time a generalized quantum master equation. And the nice thing about this is that it gives us a nice microscopic expression for this memory kernel. And this is what shows us the source of all pain. The source of all pain in this framework is the fact that we have this projected propagator, this e to the iQLT, which for a long time people struggled to deal with. For example, in the quantum dynamics community, a lot of people treated it using perturbation theories, giving rise to a beautiful theoretical framework. And for example, in the classic community, after some massaging, people just ignored that Q and set it equal to 1. But what we're going to do is take a leaf out of this beautiful work by EITAN and Cheng in 2003, where they told us, hey, what you could do is invoke the Dyson identity again and expand this memory kernel in terms of a self-consistent expansion. And when they originally derived this self-consistent expansion, they had a 2-layer self-consistency, and later Dave and I demonstrated that you could get away with only 1 layer of self-consistency, and this is just as accurate as you would have had otherwise. And the nice thing is that now you need to calculate these auxiliary kernels, K1 and K3. And what's so nice about them is that they no longer have this e to the iQLT, they have the normal propagator. And so now you can use your favorite quantum dynamics tool or even classical dynamics tool to calculate these auxiliary kernels and extract your memory kernel. But so far, I haven't shown you where this beautiful improvement in accuracy is coming from. And to do that, what I'm going to do is focus on different ways perfectly allowed by quantum mechanics of rewriting K1, one of these auxiliary kernels. So let me show you. The first thing that I'll note is that these QLs acting on the vector A, remember the vector A tells me to measure the probability of finding the electron on the blue or yellow ion. What it does is that it rotates those vectors out of their original subspace. So now we have this purple A with a tilde. And what does that mean? It means that when we make that rotation, we're going to make not only the measurement of where the electron is, but also what's going on with the polarization of the environment, what's going on with the vibrations of the molecule, what's going on with the reorientation of the water molecules around this, this ion pair. And so again, the stuff that you see on the left-hand side is the measurement that we make at time 0. And the stuff that you see on the right-hand side is the measurement that we make at the final time. So if we just rewrite this auxiliary kernel in this particular form as this correlation function of additional measurements at the initial and final time, we can call that the first closure. Now, what I'm going to do is invoke the meaning of the projection operator Q to remove Q as it appears here. It gives me 2 terms, and now I see a Liouvillean down here, which I can remove by taking a time derivative. And this allows me to rewrite this K1 auxiliary kernel as the combination of these 2 correlation functions. And the main thing is that at time 0, we are making additional measurements as to what's going on in the system, the correlations with the environment, what's going on with the polarization. But at the final time t, we are not making any additional measurements. Okay, let me put it up here. I'm going to play the same game, but now instead of removing the rotation on the final measurement, what I'm going to do is remove the rotation on the initial measurement. So I'm going to introduce the meaning of Q. I get 2 terms, and you can see over here that blue stays at the very beginning. That's the measurement at time 0. And then the purple, which indicates additional measurements, additional correlations, is only a measurement that I will make at the final time. That's the third way of writing this closure. And in the final one, you won't be surprised by what I'm going to do. I'm going to remove both rotations. And when I do so, I can rewrite this auxiliary kernel in terms of the original correlation function, the probability of finding the electron on the blue or yellow ion, and its time derivatives. Great, let me put it down here. Now, if you were to use quantum mechanically exact methods to obtain the quantum dynamics, all of these different ways of rewriting these closures would give you the exact same result. But now what I'm going to do is apply quantum classical theory to these different ways of writing these closures. And so the first one that I'm going to show you is the traditional one that EITAN and Cheng showed in their original paper. And you see this beautiful improvement in accuracy, where the green line is the approximate result, the black line is the numerically exact method, and the red line corresponds to the combination of quantum classical theory and the GQME. Beautiful improvement. And this arose when we made additional measurements, both at the initial time and the final time. So now what happens if we remove the additional measurements, those correlations with the environment, at the final time? well, we still get that beautiful improvement. So it seems like having additional information at the final time is not the crux of getting this additional improvement. What about if I remove that additional measurement at the initial time? Do I still get that improvement? And the answer is no. Now, at this point, we get an output that looks an awful lot like our original quantum classical result. And in fact, I hope that you will suspend your disbelief and believe me when I say that if I had converged these results a little bit more, they would lie exactly on top of that green line. And I did so subsequently, but I wanted to show you this because it's the one that appears in the paper. And so it seems from this plot that those additional measurements at the initial time really hold the key to this whole problem. It seems like making additional measurements at the initial time is crucial. And so you won't be surprised when I come to the final closure that makes no additional measurements either at the initial time or final time, and we get the same result that we started with. And in fact, we proved this analytically. When you use this way of rewriting the auxiliary kernels in terms of the original correlation function and its time derivatives, you will always get the same level of accuracy that you started with. And this is something that I did in collaboration with ERAN, with Lu Wang, and also with Tom Markland. Great. So this allows us to make a new hypothesis as to where the improvement in accuracy is coming from. After all, we've seen that short-lived memory kernels are not a requirement. We've seen that making additional measurements at time zero is really important. And I'm going to make it even stronger. I'm going to say that the source of improvement is exact or nearly exact additional or orthogonal measurements at time zero that look at the correlation of the projected quantities and everything else in the system. And these additional correlations inform the approximate dynamics that then get resummed in the self-consistency expansion and give you improvement in accuracy. But that's just a hypothesis. So how do we test it? Let me show you. So far, what we've been focusing on is non-equilibrium dynamics. That is, I have a photon, I bring it in, I excite an electron on the blue ion, my nuclei are in equilibrium with the ground electronic potential energy surface. And then, in this non-equilibrium initial condition that is fully separable, you can see it over here, the bath is in equilibrium, and I know that my electron is on the blue ion. Then I calculate the probability of finding the electron on the blue ion or the yellow ion as a function of time. And this is a rather straightforward initial condition to start in your quantum dynamics simulation. But what if we have an entangled initial condition of the type that you would see in an equilibrium time correlation function, where the initial condition contains the fully correlated canonical distribution, e to the minus beta h, where h contains the Hamiltonian of the subsystem, the Hamiltonian of the bath, as well as the interaction with the system and the bath. There, to be able to exactly render those initial conditions and sample them in our quantum classical scheme, we had to develop a path integral framework to be able to generate that initial condition. And the first thing that I'm going to show you are the quantum classical dynamics, the mean field theory dynamics that you would get for a particular incarnation of the spin boson model in comparison to the exact dynamics. Again, the black dots are the exact dynamics, and the different colored lines correspond to quantum classical theory. You'll see that n is equal to 0, n is equal to 1, n is equal to 2, and this n indicates the number of slices that I add into my path integral framework to converge the rendering of that initial condition. And you can see that by n is equal to 2, the dynamics have sort of converged because I've exactly, or more or less exactly, sampled the initial condition. And if you believe my hypothesis from the previous slide, that is, that the improvement that you get in the combination of quantum classical and GQME framework is very sensitive to highly accurate measurements at time zero, we should see a much bigger difference in the combination of quantum classical theory and the GQME, and that's precisely what we see. This soft red line corresponds to the coarsest of all approximations in this path integral scheme, n is equal to 0, not a very good accuracy. And yet, when we converge that initial condition with respect to n, the number of path integral slices, we see the systematic improvement of the accuracy. And I didn't cherry pick this. I mean, it's not just agreement over a short time. I've only shown you 12 of these inverse units and dimensionless units. Let me show you what it looks like over much longer timescales. Here it is. The dashed line corresponds to the exact long time limit, which I can calculate using my path integral framework. And the red line corresponds to the combination of quantum classical theory and the GQME when you formulate it in this particular way. Whereas the green line corresponds to the mean field theory result, showing a great discrepancy in the result that you should be getting. So I hope that this demonstrates to you that by now we really understand to a much greater extent how this combination of quantum classical theory and the GQME framework works. That we understand when it works, that is when it gives you improved accuracy and when it doesn't, and also by developing all of these insights that we know how to extend it to far more complicated chemical scenarios. And indeed, this has been the basis, for example, for the way in which we have applied this both in and out of equilibrium. The Markland group applied this to systems with an atomistic environment, and they showed beautiful improvements. And also, we've been able to extend this to systems with many chromophores. For example, light harvesting complex 2, which contains 3 monomers, and each monomer contains 14 chromophores. And here, what I'm showing you are the population dynamics for the excitons on one of these chlorophyll molecules in one of the monomers as a function of time. Again, the black dots correspond to the numerically exact solution. The green line corresponds to mean field theory or quantum classical theory. And in fact, quantum classical theory is very peculiar here, mean field theory. It predicts that all of these monomers get approximately the same population at long times, which would defeat the purpose of a light harvesting complex. And yet, when we combine mean field theory with quantum classical theory, you get this beautiful improvement that you see over here. And this is only over 10 femtoseconds, but the actual relaxation dynamics take place on much longer timescales, more than 1,000 times longer. Tens of picoseconds. And here we're still getting beautiful improvement for a very low cost. The cost is really low because the memory kernel itself decays by a timescale of 75 femtoseconds, a timescale that would be too thin for me to render on this plot. And then we get the rest of the dynamics effectively for free. So with this, I hope that I've been able to show you that GQMEs can be used to great effect to improve both the accuracy and efficiency of quantum classical theories that can be applied to a wide variety of chemical problems. We've developed a rigorous understanding of how and when GQMEs can be used to improve the accuracy of quantum classical theories. And finally, we've demonstrated that this potential improvement in accuracy can depend sensitively on the way that you formulate your auxiliary kernels. And I wish that I'd had the time to tell you about our recent applications to protein folding, but that'll have to be it for next time. With that, thank you very much, and I'd be happy to take any questions.
Thank you. Thank you so much. Okay, Ignacio, can this analysis be extended to driven systems?
I think so. I don't see any reason why it should not be extendable to driven systems. In fact, a time-dependent Hamiltonian is one of the new things that we're working on in terms of GQMEs, and this is something that we are testing as we go. So yes, I think that we should be able to apply it there.
EITAN, you want to ask a question directly?
Yeah, sure. So, you know, in this pathway, paper that I mentioned, we, kind of followed out on your analysis, which is very beautiful, and, show that it's actually working on, even more variations of the GQME. But you also found that if you choose forms of the kernel, where in the exponent you have QL or LQ, it makes a difference. So I was wondering if your analysis somehow can be related to this.
Yes, in fact, in the original paper with Dave that we wrote a while back, that was one of the things that we explored there. We showed that you could have in your memory kernel the Q either on the right or the left-hand side, and we developed these forward and backward closures. And indeed, the backward closure, the one that looks at more correlations at the initial time rather than the final time, tended to perform better. And The reason that I think this is because K3, one of the auxiliary kernels, would have those additional measurements at the initial time, whereas the other one would not.
Okay, thanks.
I also have a question. So is there any systematic way of checking the accuracy within GQME? In other words, I mean, right now I see there are many good possibilities and suggestions, but is there any internal kind of the more conversion or systematic method to, of course, with increasing complexity and difficulty? Do you know what I mean?
I'm not sure that I fully understand your question, but let me see if
I mean,
if
like
I understand
some kind of variational procedure. So you make
okay.
things more, I mean, so is there some kind of variational procedure to make the rate kernel more and more accurate?
We have not formulated it in those terms, and I think one of the interesting things about the combination of quantum classical theory and the GQME is that you are benefiting from this self-consistent procedure. The problem is that with quantum classical theory, there are uncontrolled approximations at some point, so they don't depend on a small parameter. And because they are non-perturbative in nature, they are quantum classical theories, you have no way of knowing a priori whether this is not going to be a very bad idea. What I've seen, and so if you're asking for rigorous mathematical analysis of when it's going to converge to something that will definitely be better, that's something that's quite difficult to say. What I will say is that one of the things that we are very interested in is how do we use the hierarchy of quantum classical methods that are going to get systematically better as a way of providing an internal consistency check that the results that you're getting are sensible.
Okay. Can you actually respond to Jeremy Schofield's question about the time reversibility, if you can answer in a short way? He put the question in the chat. Yeah, if the formalism is time reversible, it seems approximate methods of evaluating the memory kernel can break things. Is this the case?
Great question. And so what I'm going to connect this with is the ensemble that you're starting from. So you will have time reversibility if you have something like the canonical ensemble. I don't know if this is what you meant, but I'm first going to interpret it from this perspective, and you can tell me if I've misinterpreted your question. When you start from a canonical ensemble and your method is actually rendering the canonical ensemble such that you can move your propagator through that canonical ensemble, then you are not going to get any improvement in accuracy. You will always get the same accuracy dynamics that you started from.
Okay, thank you.
Thanks.
Okay, so now EITAN will host the last two talks. EITAN.
Yeah. So if the next speaker, which is ERAN, I think, can share the screen. Okay, so our next speaker is ERAN Kelly from the Max Planck Institute. ERAN, go ahead.
Thanks very much, Sugju and EITAN. It's really a pleasure to be here virtually with everyone, colleagues, former students, former supervisors, etc. It's a pleasure. So I agree with everything that EITAN and ANDRÉS just said, and I'll try to help add some color commentary and a little bit of added insight on the fringes of what they've introduced. So the topic that I'll discuss today are these quantum master equations, but with quasi-classical or quantum classical memory kernels. So I'll try to briefly motivate it, although I guess I don't need to work too hard on that at the moment, and then go into talking about quantum classical dynamics, the mapping representation, and how we construct these memory kernels, and then see, do better kernels give better dynamics and why, and talk a little bit about long time limits and future prospects. Okay, so simulating transport properties is sort of the name of the whole game that we're discussing here. And before the advent of master equations, transport properties were accessed simply through the evaluation of correlation functions that have sort of this form. And what motivates the use of quantum classical methods to address the construction of these objects is the systems we treat are very high dimensional, and these quantum classical methods scale well with the size and the complexity of the system under study. So that's one of the reasons why we're motivated to use it. And also because of the sort of generic way that they're constructed, they're compatible with model Hamiltonians for benchmarking and ab initio Hamiltonians or QMM Hamiltonians, et cetera, that you might construct to model a problem. So they're very flexible in that regard. And this quantum classical sort of family of techniques has a hierarchy, as Andrés mentioned, and that hierarchy allows one access to different levels of accuracy and computational cost. And one of the questions today is, can we use this same family of methodologies to instead access transport properties via the correlation function, but in the setup of generalized quantum master equation? So these are the sort of two mathematical structures, and what I'll talk about is how sort of one fits into the other, and the cases where this makes sense to do at all, and what you can get from doing it. So I'll talk a little bit about the quantum classical hierarchy, and sort of at the top, which is not necessarily exact quantum mechanics. It's one well-defined approximation below, the stone tablet, is what I'll call full semi-classical theory. And this has been worked on by many illustrious researchers in the field: Ray Capral, David Coker, Bill Miller, et cetera. And there are many versions of this, and at that top level, they're all sort of equal, but they come in different guises, and they may suggest different solution algorithms based on the way they look. But these theories are exact for an arbitrary quantum subsystem linearly coupled to a harmonic environment. After that, they are true approximations. There's something missing. Convenient is the fact that they can be cast in any basis that spans the subsystem Hilbert space, and the different choices of bases lead to different solution algorithms, or suggest different solution algorithms. And in practice, any of the theories that stem from this root relies on the ability to construct Wigner transforms for at least the environmental degrees of freedom, so you have to be willing to stomach that. And at the top level, the numerical properties of the existing algorithms are generally unfavorable, and this is because they are very highly accurate and contain quantum sign problems and such. But this full theory provides a formal basis for the development of further approximations inspired by classical trajectories, and so here we are. So if you step down a step from the full semi-classical theory, we have what you call partially linearized theories: the forward-backward trajectory solution, the partially linearized density matrix approach, or partially linearized spin mapping, or coupled forward-backward trajectories, forward-backward IVR, et cetera. You have a lot of partially linearized type theories. You also have fully linearized type theories like LSC IVR, or LandMap from David Coker and Sarah Bonella, PBME. And you have the familiar, let's say, Ehrenfest mean field theory. And up this hierarchy, you have increasing accuracy. And down this hierarchy, you have favorable computational scaling. And we'd like to learn the consequences, benefits, and drawbacks of using the different levels on this hierarchy. All of these techniques are based on performing a Wigner representation of the environmental degrees of freedom, basically. That's what sets us up to do classical-like trajectories. The Wigner transform is one of the ways of setting up a phase space representation for some of your system degrees of freedom. So if you take a Hilbert space with n quantum degrees of freedom, the Wigner transform gives you back a continuous phase space representation with 2n coordinates. Now, it's not the only way to do it, but it's one of the ways, and it has appeal with our classical intuition. Now, that's how we deal with the environment, or the nuclear degrees of freedom. And we may also perform Wigner over the subsystem. And how would we do that? So one of the ways we do that is by using these mapping representations. Now, the mapping representation is where we work on this the Hilbert space of the subsystem degrees of freedom and require that the subsystem matrix elements of any given operator can be exactly reproduced by the matrix elements of some mapping version of that operator in what we call a mapping basis. Now, the mapping basis states can in principle be chosen arbitrarily. Pick your favorite complete basis type thing. People have chosen singly harmonic oscillators, singly excited harmonic oscillator states, coherent states, quantum spins, etc. There's a long list. From there, you can develop a continuous phase-based representation of the mapping degrees of freedom by, for example, completing the Wigner transform, or by setting up a Stratanovich file correspondence for the spin states, for example, and achieving a fully continuous phase-based representation for your system. Now, in the mapping representation, the Heisenberg form of the full QCL equation looks like this: standard Liouville operator times some operator. Now, this full mapping quantum classical Liouville operator is not just classical. It contains a classical part, which is a Poisson bracket in the extended phase space of the system, and a non-classical part, this ILM dash. Okay, so the Poisson bracket part prescribes independent classical trajectories that evolve under a mean field type potential energy function. And this non-standard part has non-classical correlations that entangle the trajectories. This is one of the ways we can see the full solution being inconvenient. But if we make an approximation to neglect that part of the evolution, then we have what are called the linearized mapping methods, for example. Now, the full QCL Liouvillean commutes with a projection operator onto the mapping space, but this Poisson bracket part, the classical part only, doesn't commute with the projector onto the mapping space. So this means that the mapping dynamics, if you do them classically, can go away from the physically defined mapping space, and you can get problems coming in. This is one of the sources of the problems with these approximations. So let's just quickly look at the trajectory-based pictures of these dynamics. So in Ehrenfest theory, you have fully independent classical-like trajectories. This is also true in the fully linearized theories, but now they're also represented in a fully Wignerized phase space. The partially linearized theories propagate independent pairs of trajectories and thus can capture some more correlation. Now, the fully linearized theories, we made what I think is sort of an interesting contribution there by noting that the way the identity operator is treated in these theories could be helped. So we look at this projection operator onto the mapping subspace, and we see that we can write any mapping operator as being a sum of two parts, a part that's proportional to the identity operator and a traceless part. And in our modified linearized semi-classical technique, what we did is sort of just say anything that's proportional to the identity operator we'll just treat like the number one, basically. And let's see if that helps improve things, because by preserving this character of the identity operator, that may help minimize the adverse effects of our dynamics going outside the physically defined mapping subspace. So if we do that and we check out a couple of correlation functions, this is work with Max Zoller and Jeremy Richardson, we see that in correlation functions that contain the identity operator itself, we get a large improvement in the signal. So we're trying a bunch of different linearized semi-classical techniques here that basically just differ in how many times this projection operator onto the mapping space is applied at the beginning and the end of the paths. But in correlation functions that don't contain the identity, the problems are much less apparent in the method. So that's just something I'll note, and maybe we'll come up again a bit later. And so furthermore, along with EITAN and Jeremy and Max and some of the people in EITAN's group, we sort of looked more broadly at all of these linearized semi-classical methods that you can use with mapping. And last year, we sort of benchmarked them for a decent set of the standard chemical physics problems that you see these methods applied to directly, not talking about the GQME, but just to assess their accuracy on their own. So just to summarize this part, right? So evaluating transport properties the old way, quote unquote, directly from the correlation function contains two jobs: choosing your favorite approximate time evolution technique to deal with the time evolved operator, and important sampling of this initial Wigner transform of the density times the operator A. And I have this important sampling in red because there's more buried there in terms of, you know, potential problems and stuff that has nothing to do with our mapping theories or quantum classical theories, because it's not the time evolution approximation we're making. You know, that's a separate object. We can either construct a path integral to do it, or we can approximate it. But whatever we do to that side, I'll argue, has nothing to do with what we're taking as our favorite time evolution approximation. So now I get to the GQME. So we're going to supplant C of t by the GQME form by using Nakajima's Zwanzig as outlined by EITAN and ANDRÉS already. And you know, the nice thing about using the GQME as unlocked by EITAN and Chang is that you can re-express the memory kernel in terms of these partial memory kernels that you can construct with projection-free input, i.e. you can use any of these trajectory-based quantum classical techniques to calculate correlation functions that go in to K1 and K3 that go into the Volterra equation that make up the total kernel. So an example that Andrés sort of mentioned, but I'll just quickly show, is that you don't need to do this for just harmonic environments and stuff. You can do this for anharmonic environments, and it might even work. In this case, we have the electron transfer reaction. We can calculate charge transfer rates. We get improvement over the old sort of direct application of the theory, and we can ask ourselves why. And Andrés' description of why I really like, and like I said, I totally agree with it. And I'll try to just add a little bit more perspective on those same points before I finish. But you know, so you can take the mean field method, you can do tight binding type models, you can do atomistic type models, you can do ab initio if you can afford the electronic structure calculations. Here's one of those plots similar to what Andrés showed, where you can use many of these different methods. So here's a partially linearized, a fully linearized, a mean field, sort of all together against the exact results and compared against their direct application counterparts in the dotted and dashed curves. So the solid curves are the GQME dynamics for a spin boson model, and the approximate methods used directly to calculate the same signal are in dots and dashes and stuff. So there's sort of improvement across the board in this case. You can also do this with the modified linearized semi-classical theory that I mentioned, which is the same as old linearized semi-classical, but with the new treatment of the identity operator. And if you choose your memory kernel length appropriately to converge the dynamics, like in panel C, panel B has some under-converged memory kernels, for example, you can achieve good agreement again. So these are all sort of, you know, further data points on the list of methods that you can plug in and calculate memory kernels and integrate GQMEs, and they produce favorable results. Now, Andrés showed his analysis for K1 in terms of why we expect these things to be better, and I'll show the exact same fact, but for K3. And when you look at, you know, how you construct K1 and K3 from the projection-free input, there are these two options, at least for K3. And K3 contains a time derivative type object of the correlation function itself, and the correlation function itself times some scalars, basically a matrix of scalars. And these two different ways that you can construct the time derivative of the correlation function here mean everything, right? So quantum mechanically, you can move the Liouville operator through the trace that I'm showing here at the bottom because it's self-adjoint or anti-self-adjoint. But, you know, everything about where it appears matters. If it appears on the left-hand side, you have the opportunity to construct whatever's going on with that object and what it's acting on exactly at time zero in a static sense. If it's on the right-hand side of the propagator, then you have to deal with whatever approximation you've chosen. So on some level, you know, putting this work of the time derivative operator or the action of the Liouvillean at time zero gives you the opportunity to do less approximation, but getting any improvement completely hinges on your ability to sample this thing or construct this thing to sample it exactly. So for linear coupling and for harmonic environments, we're, you know, very happy because we know how to do that. In other cases, we're maybe not so lucky. And I think, you know, this issue opens up a little, you know, a more general question of, you know, when and how can we take advantage of this? When does it break down, etc. I don't have a lot of insight on that, but what I can say is that, you know, if you do everything exactly at time zero, as Andres said, then you can improve your results because you're making less approximations. And this is what we showed some time ago from mean field theory, but again, like I said, has been rediscovered now for all of these other approximate quantum classical mapping methods. So where does the most improvement come in? The interesting thing to me is that in the spin boson model, the most interesting and important improvement comes in the identity matrix containing correlation functions that go into K3 and K1. So it seems like these semi-classical or, you know, linearized methods, their failure with the identity really is their major failure. And any technique, whether it be replacing the identity operator with the number one or calculating more objects exactly at time zero, these all give you the same opportunity, but in a different context to improve upon those results. So here I'm showing you three different correlation functions. It's the correlation function of the identity operator with the sigma, x, y, and z Pauli matrices against the exact quapi. And we're looking at some substantial improvements in LSC by changing the sampling at time zero versus the evolution of the time derivative using the approximate method. So that's all in agreement with Andres said, and just a different window on the same fact. Okay, so I think, you know, this is my second last topic. I'll try to finish in 3 or 4 minutes. But, you know, one question that you could ask is, if I use better kernels, do I get better dynamics? And the short answer is usually. One thing that we've done together with Max and Graziano Amati and Jeremy Richardson is to calculate these memory kernels using the spin mapping formalism, which doesn't use Wigner for the subsystem. It uses Tritanovich files. So this different phase space construction, which seems to be beneficial in the direct application of the dynamics. And we showed that you can use it in the exact same way that you've used LSC or mean field, et cetera, to calculate this memory kernel object, and you can get out dynamics from it that are better than the underlying spin mapping as well. Here's one more example that's not spin boson, where we have a Frankel-Holstein model. It's a flat chain of tight binding sites, each with a vibrational degree of freedom. And this, you know, model can be used to study polaron formation or whatever. And here I'm showing the relaxation of the electronic kinetic energy as a function of time using Ehrenfest mean field or a set of 2 coupled Ehrenfest mean field, so this partially linearized type setup. And in this case, the underlying methods give maybe not so great approximations, but in increasing accuracy in combination with the GQME, we can approach the exact time-dependent results for this case. This is a relatively quantum case for the environment because we have zero temperature here. And lastly, on the topic of the long time limit, and this is somewhat maybe address the question that Devira asked earlier, you can access the long time limit of the dynamics of the GQME by just running the GQME really long, which is relatively cheap, or you can do a Fourier Laplace transform of the GQME and extract the long time limit of the dynamics from the zero frequency modes of the memory kernel. So for the spin boson model, you can set up this system of linear equations after you've taken the time integral and simply solve them for the long time limits of the populations and coherences. So if you do that for spin mapping or for mean field theory, you can say, what are my predictions for the long time limits of the populations, given that I can calculate the memory kernel for a certain length of time, and then look at those predictions as a function of that memory time. And what we typically see when things are behaving well or as expected is a reasonably long plateau of memory time where the steady state values are unchanged. And that's what we read off, let's say, as our prediction. Now, there are some issues that come up here. This is the set of spin boson models where we keep on making the energy bias between the two levels stronger and stronger. And an energy bias in spin boson model is one of the principal killers of the semi-classical theories. It poses more and more of a challenge because the energy transfer between the environment and the system gets larger and larger, putting more stringent tests on this back reaction force. So here, these are the steady state predictions for the populations from direct quantum classical and from quantum classical plus GQME. In all cases, we see an improvement, but also in all cases, we see some things breaking down still as the bias gets larger and larger. And this, there's technical details sort of caught up in here with sampling of the subsystem Hilbert space. So there's focused initial conditions versus full sphere sampling and stuff. I don't want to get into it too much, but the better kernels, better dynamics question is usually yes, but you still need to be careful with your kernels. I mean, I'll just go back one slide and say, if you use a very short memory time, for example, you get maybe crazy results. Or if you don't use enough trajectories to converge your kernels, you might get crazy results. Or if you really want the long time limit, you may see that the small numbers in the tails of the long time memory kernel make a big difference because it's, of course, the time integral of the whole kernel that gives rise to your prediction for the steady state limit. So you need to make sure all of your simulation parameters are verified in order to make some of these statements. Okay, so that's basically all I wanted to say. The open issues and future prospects really are technical, I would say. Sampling, Wigner representation is always an issue, okay? We know how to do it for some cases, but we're still in trouble for some others. And the subsystem sampling, Ehrenfest theory is a good example of this, where Ehrenfest theory tells you how to do dynamics. It doesn't tell you how to sample the subsystem Hilbert space. And your ability to do that sort of cleverly or completely has a major impact on the accuracy of your GQME approach. And like EITAN said, I'm very excited to push or be pushing these techniques into the sort of milieu of spectroscopy and response properties, as well as just looking at these sort of benchmarky population dynamics things. But a lot of the physics is embedded there, so that's why I decided to talk about that today. So I'd like to thank EITAN and Sugi in particular, but also the people here in Hamburg and in Japan, my collaborators in Michigan, Max, and also EITAN there, Graziano and Jeremy in Zurich, and the local cluster here in Hamburg for for having me and you for your attention. Thanks very much.
Thank you very much for a beautiful talk. So, not see any. If you have any questions, please put them in the chat. Why is my talk showing? Okay, I can, I guess, start with a question. So I put a question in the chat, but I will ask another question first. You know, there is about the Wigner, we know that if you do the Wigner of A rho as opposed to the Wigner of A times the Wigner of rho, it makes a difference. I
would say a crucial difference.
A crucial difference, yes. Do you see a connection between this and what Andre told us, basically, and you told us too, about, okay, all those forms of the inputs, how they affect the, because it's also in the initial time and you have this kind of correlation. So is this the same kind of effect, basically?
Yeah, I would say yes, exactly. I'll just maybe try to get there. Yeah, I mean, everything rests on the red phrase, right? Important sampling that object. Now, generally speaking, as you said, that object comes, you know, once you take Wigner, you have the exponential of the Poisson bracket operator in between rho Wigner and A Wigner. And the power series expansion of that will bring in imaginary terms, for example. So the structure of that thing has a huge impact on how the memory kernel that this correlation function gives rise to will behave. 100%. And I think that, you know, André's work on basically showing how you can construct the exact Wigner for a particular case in path integral language is one of the most motivating things to me on this topic, because I think, you know, while we've been on some level avoiding the fact that we don't really know how to do exact Wigner transforms analytically for non-harmonic cases or beyond linear coupling, et cetera, I think we know where we can start. And I think this is important.
Yeah, I mean, just to reiterate, I mean, we have found over the years that, you know, from force correlation functions to Fabrice Golden rule correlation functions, that this can make or break basically what you're doing. And I would like to emphasize this because there are many people out there who sometimes say LSC does not work, but what they do is they do the Wigner of the product of the Wigner as opposed to the Wigner of the products. And this is often, like you said, this is really the red kind of writing on the wall, right? Of how you, yeah. I don't see any other questions in the chat. I have another question, but if somebody else can ask, it's probably better. Okay, so I'll ask. We didn't touch upon this much. Oh, there is a question. Okay, Jeremy Schofield. This is related to time translational symmetry of correlation functions. Is this a question or a comment?
So, I mean, maybe that was following up on Jeremy's point at the end of the previous talk, but I mean, I agree. You know, somebody else after your talk, EITAN, asked, I forget the name now, about NRPMD plus GQME. And I think our understanding is if you have a dynamics method that preserves time translational invariance, you cannot benefit from this GQME shuffle that we've been discussing, because the action of the Liouvillean in the time derivative part won't be incorrect like it is in mapping or Ehrenfest or whatever. We have the opportunity to shuffle that into our initial time and get something right that we wouldn't have got right before. But with methods that preserve time translational invariance, you get what you get. And I think the only tangible benefit to the GQME there will be a shorter timescale object to construct at the price of maybe more matrix elements and maybe more trajectories and maybe smaller time steps. But it begins to become technical.
I guess I'll ask one more question if Sugi is okay. One more question. So this is something that I mentioned, and I think maybe, but we didn't really talk about it in detail, so I just want to hear your thoughts about this. This is about the numerical instabilities with some methods and not with others. Like sometimes you get a memory kernel, okay, starting to oscillate. You mentioned the plateau, okay, but sometimes there is no plateau. And I was just wondering if you can, comment on this, your thoughts.
Right, so one of the things that I guess one takes as implicit truth when you start to develop a GQME approach to a problem is that the language of the GQME will be useful somehow, that the memory kernel probably decays or whatever, potentially, right? And if I take a small closed system, like I showed this Holstein chain, right? We had to do 10 or 20 sites before we had a bath of vibrations, right? If I take the 2-site Holstein model or something, I have 2 vibrations and 2 electronic states. And there, the GQME doesn't really help me per se, because I don't get anything that really decays. And in some ways, it's a rewriting of the problem, and I can maybe correct some of those, initial time things. I can maybe get some better dynamics, but I don't know necessarily that I'm packaging the problem in a short time effort versus looking at the total time scale of the dynamics. And, I feel like this for sure has implications in thinking about transport properties, because, in chemical rate theory, or if you're looking at diffusion constants, you expect at some point a steady state behavior to set in. And if we're not looking at a system in one of those regimes, then I guess what we find is that we have some highly non-Markovian memory kernel. And, that's the sort of, let's say, cheap introduction to what ERAN will probably talk about, right? These other non-trivial cases. And there, we're probably better off doing some exact quantum mechanics so that you know what's going on and not have quasi-classical kernels telling you things that might not be true.
This note, okay, it's a good segue to ERAN's talk. So ERAN, if you can, Aaron, you should stop sharing, I guess. And so this is ERAN RABANI from University of California, Berkeley. ERAN, take it away.
All right, thank you. First, I want to ask if my screen is shared in screen sharing mode.
Yes, we can see it. Yeah.
All right, good. So first, I want to thank you, EITAN and Sagi, for putting this together and for including me in the program. And I also want to thank all 3 speakers preceding me today for beautiful talks that actually are going to really help me be able to deliver my talk in 30 minutes. And so what I am going to talk about is long-time memory effects in a localizable central spin problem. I'll motivate a little bit why I want to talk about this. And to tell you the truth, there's a lot of interesting physics that people have considered in systems like that, but I am less interested in this talk in the physics and more in the dynamics themselves, and so and how to describe the dynamics. So this would be the focus. So we've heard, I think, throughout this workshop about system bath Hamiltonians, and these are the typical. Let me see if I can take a pointer. These are the typical models that we use, and often we would describe the bath, which is what we're not really interested in its dynamics, either using a set of harmonic modes, or if you're interested in other kinds of descriptions of bath, like in molecular electronics, you would use a fermionic non-interacting bath. But the key is that in these cases, you use a non-interacting bath. And this Hamiltonian itself actually, even though you simplify the description of the bath, gives rise to quite interesting physical phenomena. We know that we use the spin boson model in this context to describe electron transfer reactions. If we want to understand Coulomb blockade or Kondo effect, we would include correlations in the system Hamiltonian. But in all of these cases, the bath is always quite simple and easy to describe. And we also have an arsenal of methods, and we've talked about reduced dynamics, but there's an arsenal of methods that you can use today to be able to address questions in various different regimes of interactions to describe the dynamics of the system. But as probably my title suggests, I am now interested also in situations where the bath is not described by a simple non-interacting picture, but actually is an interacting bath. And the kind of phenomena that interacting baths can describe, which is missing in non-interacting baths, is of course different phases and also support transport of particles or energy. And so one specific example, which will be the focus of this talk, is what's called the many-body localized bath. So quickly to explain to you this, I'm going to consider an XXZ Heisenberg chains of spin halves on a lattice, and this would be the bath that we're going to analyze its many-body, its transition from a many-body localized system to a thermalized state. This phenomena, of course, occurs at very many different models, but I'm going to focus on this one because this is the bath that I'm going to consider when I want to couple it to a central system. And so following a unitary transformation, or a quench, if you want, in unitary dynamics, the system can either relax to a state on the lattice that has the same magnetization, and this would be shown up here in the upper panel. In other words, I start from, in this particular case, from a nil state where the lattice is ordered with spin up, spin down in this way, and if and upon a unitary transformation, we could the system would relax to what we call a thermalized state, where on average all the different magnetizations of each side is the same. But on the other hand, in some situations, the system may also relax into a, or may have, you would say, may remember more about its initial state and would be stuck in what we would call a localized, a many-body localized state, by which the system doesn't relax to an equal population or an equal magnetization on each one of these sites. And so you can control this, whether the system relaxes into a thermalized state or a localized state, by changing parameters in this Hamiltonian. And one of the most significant ones is, of course, the distribution of this order that you introduce into the on-site fields. And so, for example, if the distribution is quite small, upon a quench from a nil state, you would end up in a thermalized state. But if you increase the value of this order, then you will induce localization in the system. And in the same way, you can induce localization or a transition from a localized state to a thermalized state by increasing the coupling, the many-body coupling here. And this is why it's called the many-body localized, because you can induce a transition from a localized state to a thermalized state. I'm not going to go much into the physics of this. I just want to mention that this is different from Anderson localization, which occurs here at a value of zero value of Jz, namely for the integrable case, and the fact that you still see a localized phase state when you increase the many-body interacting term is basically the main question that people have wondered in this field about. And so we are interested in a bath that is described, by this type of a Hamiltonian, where it can undergo a transition between a localized and a thermalized bath, but we also want to couple it to a central system. And one of the ways this could be done is using this device here, where people can actually build resonators, where in this particular case, region B is coupled to 11 spin sites. And this problem can be mapped onto, or this experiment can be mapped onto exactly an Hamiltonian that looks like this, where the experimentalist can control everything in the system, including this order. And so, and this is a small system, of course. They can now do much bigger systems where the number of sites that the centrally spin system is coupled to can be much larger. And so if you think about the geometry of this system, we have a central spin that is now coupled to all of the other bath spins. And this problem raised many different questions about the physics, which I'm going to ignore in this talk and just go and discuss what we want to actually study in a system that looks like this. So I'll write the Hamiltonian in a second, but the idea is that I have a central spin that is coupled to all the different sides. And so the question is, the first one is, how do we model this? The dynamics of the system, the thermodynamics is a different question, but we are interested in how the system approaches its steady state, or whether it gets stuck in a many-body localized state, and how the central spin system actually affects the transition from a localized to a thermalized state. In addition, we want to know what the timescales are to approach a thermalized and the localized states, and how and whether the system approaches that through you know, an exponential relaxations, or whether the dynamics involve a much more complicated description. And finally, can we observe anything about the non-trivial bath dynamics in the localized versus the thermalized phase in the dynamics of the central spin system? So the way, the model Hamiltonian that we are going to consider would be the same Hamiltonian that I've described before, a system bath Hamiltonian. The bath would be exactly the bath that we've just discussed, which can undergo a transition from a localized to a thermalized phase. The system is just a two-level system, and tau z is a spin, is a Pauli matrix for the system degrees of freedom. And then the coupling is going to be taken in this form. I have not invented that form. That form was first discussed in this paper. But the idea is that I rescale the coupling by the size of the system to make sure that I can actually maintain localization, a transition from a localized to a thermalized phase. So what you can see here is the phase diagram that was actually basically extrapolated to the thermodynamic limit from a calculation on 16 sites only between the localized and the thermalized phase as a function of the strength of this order and as a function of the system bath coupling gamma. So as you increase this order, you're going to go from a thermalized phase to a many-body localized phase as before, but you can also increase the system bath coupling and undergo a transition from a many-body localized phase to a thermalized phase. And so what we would want to study is the dynamics along this line as we go across the transition, and whether we can see signatures of these transitions in the dynamic of the system. And so what we are going to do, since we're only interested in the dynamics of the system to a great extent, is that we're going to use the Nakajima-Zwanzig equation. But unlike the traditional approach that we basically project the bath out of the dynamics and describe an equation for the reduced density matrix, in this case, we're actually going to just look at the dynamics of the spin down population. So we're projecting onto the spin down itself to obtain a scalar Nakajima-Zwanzig equation with a memory term that is formally given by this equation. And we've heard today many different ways of how you can obtain that memory term, a memory kernel. But since I'm looking at a transition, a quantum transition from a many-body localized phase to a thermalized phase, and my system is highly quantum, is a two-level system, I'm actually going to restrict myself to a fully quantum mechanical description. And so one caveat that I want to mention in this respect, which was a comment that we received from the referee of our paper, that our equation is wrong when we write the equation in this way, has to do with the fact that you can actually generate an equation for the say spin down population as a function of a Nakajima-Zwanzig equation. You can formulate that, and you can have different memory kernels that would give you exactly the same dynamics. So the memory kernel itself is not a unique object. And a simple example that we worked out in a paper that we published with David Limmer, and of course Nathan is my student, is my former student working on this, is that we consider two ways to write down an equation for a two-level system. There's no bath whatsoever, but you can still trace out the upper state and obtain a Nakajima-Zwanzig equation for this, the lower states, the zero state. And you can do the same thing in a different way. You can write down, say, the dynamics and project out only on the populations. In this case, we projected out, and in the upper case, we projected out the populations onto the ground state population. So we projected out the coherences and the upper state population, but you can just trace out the coherences and remain with just the populations and then impose that sigma 0, 0 plus sigma 1, 1 equals to 1, and you get a different equation. This is a homogeneous equation. This is not. And it seems like, how can you have a memory kernel which is inhomogeneous, give the same dynamics with a memory kernel that is homogeneous? And of course, we've shown analytically that they all give exactly the same dynamics. But if you look at this memory kernel, which is k of tau, and if you look at the other two, because there's k11, which I write k1 here, and k00, which is k0, you can see that all three memory kernels here actually look quite different, even though they generate the same dynamics. In other words, the combination of k1 and k0 generate the same dynamics for sigma as k0 here. And that fact that the memory kernel is not unique was, at least to me, quite surprising and new. Anyhow, in practice, how do we do the calculation, and why do we want to use this formalism has to go to the fact that we want to simulate everything quantum mechanically. But even if we take the best quantum mechanical solvers of say impurity problems like that can handle correlated baths, even if we do that, we typically would run out of steam, particularly in describing near the transition between the many-body localized phase and the thermalized phase. And indeed, we have tried to do that with, for example, MCTDH recently, and we couldn't converge the dynamics in the thermalized phase. So the Nakajima-Zwanzig formalism, where we, instead of calculating directly the reduced density matrix or whatever element you'd like to calculate, we actually calculate the memory kernel, could provide advantages if and only if the memory kernel is short-lived. And in that case, you can generate the memory kernel from an exact solver like MCTDH, and then plug it back into the Nakajima-Zwanzig equation, and whatever type of analysis you want to do, since that's a very simple equation to solve, you can solve it in many different ways. This is an example that we've done for an open quantum system where we can use MCTDH exactly to compute the dynamics in a fermionic, in a non-interacting fermionic bath. And what you can see is that if you take a cutoff in the memory that is on the order of, in this particular case, 100 femtoseconds, you are basically converging the dynamics on all time scales, even though the population dynamics continue to evolve on an order of magnitude larger. And we've done, since 2011 until today, we've done many different examples by which we leverage on the short-lived memory kernel for particularly driven systems. And we basically show that you can generate the exact dynamics or the converged dynamics by truncating the memory with a cutoff time. So we wanted to use the same ideas for this particular system. So we basically calculated the memory function by using an exact solver, and we limit ourselves for the analysis that I'm going to show you for small enough systems where we can actually do exact diagonalization. So our approach, so we can generate the exact dynamics and then calculate the memory from the exact dynamics in various different ways. Our preferred approach, which we published, I think, in this paper, is to use just the populations of the system for different initial conditions, which is an easy observable to calculate in MCTDH. And from just those populations, we can generate the memory. And if you want to know how, you can read this paper. Anyhow, what you can see is that we have to do this over different system realizations. And what I'm showing you here is the average memory kernel as a function of time in various units that we like to work in, and also the distribution of memories. And of course, the distribution of memories for each realization never decays to zero because we have a finite system, so there are recurrences and so forth. But on average, and if you're interested in the average dynamics, which is what you often can measure, you basically do relax to a small value. Now, this is the localized phase, and you can see that the memory in the localized phase, and this is in the thermalized phase, and the memory in the thermalized phase look quite different. And this is actually reminiscent of being localized, these high oscillations in the memory at intermediate times. This is a reminiscent of being in the localized phase, and because these oscillations decohere relatively slowly compared to what you find in the thermalized phase. But in both cases, on average, it seems that the memory decays to zero quite fast. So maybe we could use the cutoff approach to calculate the dynamics of the system. One thing that I want to emphasize is that when we calculated the memory for individual realizations of the disorder in the system, we found out that the memory doesn't decay to zero, there are fluctuations. But there are also situations by which, and you can see it here perhaps, by which the memory showed an exponential growth in time. And this was a mystery to us because we've never seen something like that when we worked with thermalized baths. But I have to remind you, we're starting from a high temperature Neal state. And so it's actually physical, and we've proved that this could actually happen in some situations. And we know in which situations and approximately this would happen depending on the coupling in the system. But what's interesting is that we could correlate this exponential growth that doesn't happen if you average over the memory, but happens at individual trajectories. We could correlate that to some extent with a transition between the localized and the thermalized phase. But that's a side note that I wanted to mention. And so the next thing we wanted to do is use the memory function, as I said, and use a truncation. And one thing that we can see is, of course, that we cannot use a truncation on the memory of each individual realization, but on the average, we might be able to. But the question is, there are two ways to define the average memory. One way would be calculate the average population and calculate the memory that corresponds to the average population. And in another way, calculate for each realization the memory, average that, and then calculate the population that corresponds to the average memory that was calculated this way. They should be the same if your random process is linear, but this is a nonlinear equation when you do the dynamics. And so in principle, they might not be the same, but it turns out that for our calculations, the difference was so small, which both in the localized and in the thermalized phase, which allowed us to use both formulas and to do the analysis that I'm going to show you. And since I can't see the time, EITAN, how much time do I have? I guess
it's 8 minutes.
5 minutes, you said?
8.
Okay, all right, good. So that's great. So let's start with the short time analysis, which is typically something that is not completely interesting, but in this case, we wanted to see even whether there are at short times effects that are correlated with the state of the bath. Namely, would we be able at short times already to observe differences in the dynamics when we compare the thermalized and the localized phase? And so we did a short time analysis, of course, and what we found out that in the thermodynamic limit, the short time behavior, this could be fit to to second order, of course. This has this form, and tau is the width of this, if you want, or the second time moment. And the second time moment for this model can be approximated in this form. or this is an exact form, by the way. And what you can see that in the thermodynamic limit, when we take L goes to infinity, we actually find that this time depends only on the width of the disorder in our system, but not on whether the system is in the thermalized phase or not. We've already discussed the intermediate times, and what I'm showing you here are a set of calculations from various different couplings going across from weak system bath coupling to strong system bath coupling, going across the transition from a thermalized to a localized phase. And we've discussed these intermediate time oscillations that seem to be very pronounced in the localized phase, and that would be expected. We made an analysis of what would we expect these frequencies to be like, but we couldn't understand, we couldn't be able to predict what would be the decoherence time analytically. Well, we did numerically observe that the decoherence time of these oscillations is much faster in the thermalized phase. And interestingly, if you look at the dynamics of the populations at intermediate times, you don't see anything that tells you a big difference. You just see a continuous decrease in sigma 1,1. And you know that sigma 1,1 has to approach the equilibrium, the value of a half when you're in the thermalized phase, because that would be equal population with the spin at high temperatures. That would be what you would expect. So based on the populations of the system itself, you would assume that these all are localized to some extent. And the dynamics seem to be a little bit boring and show pretty much the same effect, but the memory kernel shows a very different and pronounced effect. But to understand how the system approaches its long time limit, and particularly to address the question whether it's localized or thermalized, we had to use, we had to develop an approach that that was to account for power law decays of the memory at very long times. So let me explain where this comes from. In principle, I just quickly want to show you these trajectories. What we can see here is that we have exponential growth of the memory, both in the thermalized and in the localized, but it's more pronounced in one phase than the other. But on the average memory kernel, we don't see any exponential growth, which suggests that for any memory with an exponential growth, there's also another configuration which cancels this, and we can actually analyze this in Laplace space, and we find that this is indeed the case. So if there is no exponential growth or decay of the memory, this means that the memory has to decay as a power law. And to get the long time limit of a memory that has a power law decay, that's very difficult, because if you use the truncation schemes that we've used before, namely a cutoff time, that's not going to work. So instead of doing this, Nathan developed an approach that we do it in Laplace space. We can simulate our system up to this time, but this is in Laplace space. So this would be the correspondence time that we do in real time. And then we use an extrapolation scheme that not just calculates the value of sigma, which is what we've used before at this time in Laplace space, which is what we've heard in the previous talk. But we now also try to fit this to a dependence that looks like this, which allows us to extrapolate to the long time limit to describe with this term here, z to the power of psi, the power law relaxation of the memory. We don't have a proof that it has to be power law. We just have an argument that it has to be power law. But when we use this scheme, what we find for these systems in cases where we can calculate the steady state value from exact diagonalization directly is that it actually works pretty good. What's interesting is that if you don't use this scheme, then you get results that are quite off from the steady state value. And there's quite a lot of dynamics that occur on timescales beyond our cutoff time, where we need the extrapolation to account for the relaxation of or the long time limit of our population. And finally, what we can do is we can then use this long time limit and fit it to a power law to understand how you can approach a thermodynamic limit. And what you can see is that in the thermodynamic limit, the correlation, the value of P in the thermalized phase has to be equal to 1/2. So I'm showing you deviations from this. These are the systems that we could study, but you can see that this behaves very well as a power law and will decay to a value of 1/2, but quite slowly with the system size. So if you actually want to approach a thermodynamic limit, that also occurs quite slowly in the system. So with this, I'm going to stop and just summarize that. I'd say when we want to describe correlated systems, correlated baths, interacting baths, then often in the quantum limit, we would often need to resort to the Zwanzig-Nakajima formalism to simplify the description of the dynamics, but there are complications that arise in the bath, and this is not only in a correlated bath, but power law decays can also occur in the spin boson model. But when you have long power law decays of the memory, you can try to use this approach in Laplace space to extract the steady state values, which would help you understand in this particular case whether the system is thermalized or localized. Finally, I just want to thank Nathan, who graduated and is a postdoc with David and Andy Millis at Columbia, and my collaborators from Michael Toss Group, and Hans-Dieter Meyer, who also gave us the MCTDH code to do these calculations, and Michael, who is a professor at Texas, who was involved in the first paper on the MCTDH work. And thank you.
Thank you very much for a beautiful talk. So we have several questions. I'm going to skip mine for the sake of others. So Sugi asks, what is the physical meaning of exponentially growing memory?
Yeah, that's hard to understand. You have to remember the memory is exponentially growing, but it's oscillating too. If it was just exponentially growing, this means that the system would have just stopped. You'd have an infinite memory. The system cannot move. But this is oscillatory, so it's just the envelope is exponentially growing. We haven't analyzed the physical meaning of that. It was surprising, and I thought it was an artifact of our dynamics, but we proved that it's not. And we've done the same calculation in Laplace space and found all the different poles of the memory, and they agree exactly one with each other. So it seems like it's a robust approach. We need to work more to understand it.
Just to follow up on this, so you said that there's an experimental system, okay, that this is supposed to mimic. Do you think if you do this in the experiment, you're going to get exponentially growing memory?
No, because they can't recover just an individual realization like we do. They have a system that fluctuates. They can control to the extent of fluctuations, but they measure the average quantities, the average populations.
So just to follow up on this, what gives rise to an ensemble of memory kernels as opposed to one? Because in all the previous models we have seen in previous talks, it's just only one memory kernel, right? You have an ensemble of them. So this is called disorder?
Yes. So maybe I didn't mention this at the beginning.
You have an ensemble of Hamiltonians, basically.
Yeah. No, so I have to calculate. It's just like okay, to induce Anderson localization, I have to introduce disorder to my non-interacting Hamiltonian. So the disorder is what drives the localization. In the case of Anderson localization, you need to introduce a very small disorder in one dimension to localize the system, but you need disorder. In the case of a many-body localized phase, you need larger disorder to see a transition to the thermalized phase. Small disorder. If you introduce small disorder, you're still thermalized. So you need large disorder to see a localized phase. And so how do you simulate the dynamics when you have disorder? You either go to the very large system and then you have self-averaging, that would be an equivalent way, or you just take a small system like we did or like the experimentalists did and model each realization separately and average over that. That's assuming that there's no coupling between disorder, namely that the change in the disorder and the internal dynamics are decoupled completely, different time scales, which is the case.
So why can't you do in the experiment the realization that gives rise to those, infinitely growing memories?
Because they don't control they only control the disorder strength, but not the disorder. So they basically can't measure one realization. Their instrument is not fast enough. So they measure the average response.
But if they could, they would measure infinitely growing.
If they start from our nil state, that's what they should do. Yeah, that's what they would see, definitely.
There is a question from Dvira, which I think is related to this, but if it's not, maybe Dvira can ask. Okay.
Should I read the question?
You can read the question too, yeah.
Ron, very interesting. If I understand correctly, you begin with a nil state for the interacting bath. Can you explain then the notion of temperature in your work? Okay, yeah, I don't have temperature here. It's like, you can think of it as very high temperature if you start from a nil bath. So I haven't described temperature in anywhere in my talk. What I did is describe how you can induce transitions by changing the parameters in the model. But it's always a high temperature. So just to explain, Anderson localization occurs at any temperature. All the states become localized. So that's why to see Anderson localization, there's no temperature effect.
There is a question, interacting buff usually has a chaotic energy spectrum. How to prepare the initial state for the simulation?
This specific one, as a matter of fact, if you don't introduce this order, and there's is integrable model, so it doesn't show it. But as I said, what we do when we simulate the initial condition for the bath, we just take a nil state. So a nil state will just be, it was back here. Sorry, it would just be what we start as. We label our bath spins from 1 to L, and we just take opposite values of the spin, of the magnetization on each state. So sigma z would be up, down, and that's our initial state.
Yeah. So I think we can add the official discussion of this specific one here, Sugi, right? And maybe transition to the general discussion.
Okay.
Or do you want to stay? Actually, I have a question to kind of maybe start this.